We've all had this dream, right? Humanity becoming a multi-planetary species, setting up shop on the moon or Mars. It's a huge part of our science fiction, our vision for the future. But what if the biggest thing stopping us isn't the rockets or the fuel, but our own bodies? Today, we're going to look at the brutal biological truth of space travel and explore a pretty wild idea that our destiny isn't on planets at all.
Wow, just let that sink in. This quote, it completely shatters that heroic image of astronauts returning, waving to the cameras. The reality for anyone who spends a long time up there is often just total physical collapse. They're so weak from weightlessness, they literally have to be carried out on stretchers. It's a shocking picture, and it perfectly frames the problem we're up against.
And that's the core issue, isn't it? For millions of years, every part of us, our bones, our hearts, our brains, has evolved to work perfectly under one specific condition: Earth's gravity. It's the constant pressure we've always lived with. So what happens when you take that away? Well, our bodies don't just adapt, they start to come apart. Let's see how. Okay, so let's meet enemy number one. It's not some scary alien, it's the environment itself. It's the simple fact of being weightless. We call it microgravity, but its effect on the human body is absolutely massive. It's like a silent, invisible force that just starts dismantling you piece by piece. Now, I know what you're probably thinking. Well, can't they just, work out a lot? And believe me, they do. Astronauts exercise for hours every single day on some seriously advanced machines. But here's the kicker. It's not enough. It helps, for sure, but it's just a Band-Aid. It can't stop the fundamental damage that happens when your body isn't fighting gravity 24/7. 1%. That might not sound like a huge number, but get this. That's the amount of bone density an astronaut loses from their legs and spine every single month in space. To put that into perspective, that's the same rate of decay a person with severe osteoporosis loses in an entire year. And all that exercise, it doesn't stop it. And it's not just the bones. Your muscles, especially the big ones in your legs and back that you use to stand up, they just start to waste away. You can lose up to 30% of your muscle fiber. The body's logic is brutal and simple. If we're not using these muscles to hold us up, why keep them? Let's get rid of them. So this really drives the point home. Even with the most intense workout routines imaginable, astronauts come back to Earth way, way weaker. Exercise is absolutely critical, but it's basically just slowing down the inevitable. It cannot replace the real thing, the constant everyday work of just living on a planet with gravity. And if you thought bones and muscles were bad, the problems go way deeper. Your heart doesn't have to pump blood uphill anymore, so it gets weaker. Your brain gets all sorts of confusing signals from your inner ear, messing with your balance. Your immune system takes a nosedive, so old viruses you've had, like the one that causes chickenpox, can actually wake up and reactivate. Even your senses of taste and smell get weird, leading to something called space anorexia, where nothing tastes good and you just don't want to eat. So, microgravity is a huge problem, but there's another invisible danger lurking out there, especially once we leave Earth's orbit. And honestly, this might be the real showstopper for any long-term mission. I'm talking about space radiation. Here on Earth, we're living inside this amazing protective bubble called the magnosphere. It shields us from almost all the nasty radiation flying around the solar system. Even the ISS is mostly inside this shield. But the second you head for the moon or Mars, you're leaving that bubble behind. You're out in the open in a constant storm of high-energy particles. Just look at this chart. The difference is staggering. Down here on the ground, we get about 3 units of radiation a year. On the ISS, it's about 182. But on a mission to Mars, you're looking at almost 700 units a year. That's over 220 times the radiation we get just living our lives. It's a completely different and profoundly more dangerous environment. And this radiation comes in 2 nasty flavors. You've got solar flares, which are these sudden, violent bursts from the sun that can hit you with a massive dose all at once. That's the acute danger. But then there's the really insidious stuff, galactic cosmic rays, or GCRs. Think of these as a constant, steady drizzle of high-energy bullets coming from all directions, all the time. You can't predict them, you can't dodge them, and they do long-term damage. And that constant drizzle really adds up. This number, 2.8%, is the potential increase in your lifetime risk of dying from cancer for every single year you spend in deep space. So a trip to Mars and back could add more than a 10% increase to that risk. That's a fundamental barrier. You can't build a colony on that kind of risk. Okay, so the problems are huge. Our bodies fall apart without gravity, and we get fried by radiation without a magnetic field. So what do we do? Well, if we can't change our biology to fit space, then we have to change the space to fit our biology. And that leads to some absolutely massive engineering challenges, all aimed at one goal: recreating Earth out there in the void.
The answer to the gravity problem is actually an old sci-fi staple, artificial gravity. It's a pretty simple concept, really. You build a big, spinning wheel. The force of the spin, centripetal force, pushes everything to the outer rim. And voila, you have a floor. You have an up and a down again. You have gravity. But, and there's always a but in space engineering, the physics gets tricky. If you spin is too fast, everyone gets hopelessly sick from something called the Coriolis effect. So you have to spin it slowly, no faster than about 4 times a minute. And to get a full 1 g of gravity while spinning that slow, you need to make the structure big, really big. We're talking a radius of 56 meters, meaning the whole spinning thing has a diameter of 112 meters. That's longer than a football field.
All right, so what about radiation? The solution here is, well, it's a lot less elegant. We can't build portable magnetic fields, so the only real option we have is brute force. Just put a whole lot of stuff between you and the deadly rays. Water, soil, metal. The key is just mass. Lots and lots of mass.
And this is where you really see the scale of the challenge. Protecting against a solar flare is one thing. You can build a small storm shelter in the ship. That takes about 2.5 metric tons of shielding. But to protect against those constant cosmic rays, you have to shield the entire habitat. And that requires a mind-boggling 78 metric tons of shielding for every single person on board. So let's put it all together. To live safely in deep space for a long time, you need a giant spinning structure to create gravity, and you need to wrap that structure in tens of tons of shielding per person. When you accept those 2 requirements, it leads you to a very surprising and maybe even controversial conclusion about where humanity's future in space really is. And here's the thing. For all our dreams about Mars, the red planet just doesn't solve these 2 core problems. Its gravity is only about 1/3 of Earth's, which is probably not enough to keep us healthy long term. And just like the moon, it has no global magnetic field to protect us from that cosmic radiation. Living there would mean living underground and still having your body slowly break down. This quote just nails it. It raises a fascinating question. If you have to build a massive, shielded, rotating habitat just to survive on Mars, probably buried deep underground, why even go to Mars in the first place? Why not just build that habitat in free space, where you can dial in a perfect 1 g of gravity and have way easier access to resources? The argument is that our future isn't on other worlds, but in worlds we make ourselves. This suggests a totally different roadmap for getting into the solar system. Step 1, let's build one of these spinning habitats close to home, in low Earth orbit, where we're still protected by Earth's magnetic shield. Let's get the tech right. Step 2, use that technology to build ships that can give us gravity on the long journey to places like Mars, so we don't show up as weak as kittens. And then, only then, Step 3, build the giant shielded self-sufficient habitats in deep space that could be our first true off-world homes. And this just flips the whole idea of space exploration on its head, doesn't it? It suggests that maybe our destiny isn't to try and adapt our very fragile bodies to alien worlds they were never meant for. Maybe our destiny is to take the essential conditions of our own worlds, gravity, air, protection, and learn how to build that anywhere we want to go. The challenge isn't about discovering a new Earth, but about creating one.